And now we're going to connect our discussion on the Bootstrap with the refresher we just had on linear modelings in the previous section, because the point was precisely to bring the ideas of bootstrapping into the work we've done up until now with model parameters, with computing parameters for our linear models. So, as we saw, theta hat, which is given by this particular expression, which is the solution to our normal equations, is our estimator of the true value theta star of the parameters that we have no access to right now. This estimate is going to depend obviously on the training data, right? The design matrix is built from features that we gathered from our data, and the observations Y are part of our data set. So what we want to do is ask ourselves, well, what would happen if we had gotten a different set of data to train the model with? What would happen to our estimates, right? So now you should see kind of these two trains of thought converging in the course of our discussion of linear models and how we go about constructing our parameter estimates together with what we've just gone through on the Bootstrap. If we bootstrap our training data, then we can use each of these new samples of the data to fit a slightly different linear model. Obviously, some of the samples will be a little bit different through the bootstrap process, and this will give us a set of theta hat estimates, one per each bootstrap training sample. And now we can look, therefore, at a distribution of our parameters, and we can construct, therefore, confidence intervals for our parameters. So this will be a way of understanding a little bit more some of the properties of our model and assessing the quality of the model. In general, as a quick reminder, we have a structure for that we assume for the underlying physical data generation process to be given by a linear combination of features with an intercept plus random IID noise that we have no control over and no access to, right? These are the starred values of the parameters, the true values of the parameters. And what we do is, assuming that this is true, we construct a numerical model after computing our estimated values of theta hat that we use to make predictions, right? This is the mathematical expression that we use to make our predictions. And now what would happen if one of these theta hat parameters, let's say theta 1, the first non-intercept term, was 0? That would mean that the associated feature has no effect on the response, right? And that's an interesting question to ask. And that is the kind of thing, if you go back to the beginning of this lecture, where we want to understand, for example, how does in general a given feature impact our understanding of the phenomenon. What happens? And if a given feature has no impact on the observations, then we may want to know that. But the question is then, how can we know whether we can with some certainty say that a given parameter is 0 or not, since in general we probably will not get exactly a 0, right? So what we would like to know is whether we think with some confidence that theta 1 star, the true value of the parameter, is 0. We are going to get an estimate of theta 1 hat from our samples, which is unlikely to be itself 0. So what we would like to know is what would happen if we had access to many more samples. And so if our sample is good enough to be representative of what we think is happening in the real world, we can use the Bootstrap on it, estimate fit our model, estimate our theta 1, provide our estimate for theta 1 star, which is theta 1 hat. And then what we can do with these is construct a confidence interval, and we can ask whether the confidence interval includes 0 or not. If our confidence interval at a given confidence value includes 0, we would say that, well, we think theta 1 star is not statistically significantly different than 0. And otherwise, we think it is significantly different from 0. And this is an important sort of conclusion that we may want to draw about what is happening in the world, because we can say, well, that particular feature doesn't actually matter, even though maybe from the one data set that we have, there is some effect. The actual value of theta 1 hat that we produce is probably from our sample is probably not equal to 0. But this gives us a way to draw a conclusion about what we think with that level of confidence is true in sort of the real world, in the underlying data generating process. This all can be couched in the language of formal hypothesis testing. The Data 8 textbook does a little bit of that, but we will not focus on that today. And it's worth noting that this will work, and we're talking about theta 1 hat, and we construct a linear model, but the same idea will work for any other feature, and it works both in linear and logistic regression models. As you've noticed, we haven't really make any very specific use of the properties of linear or logistic regression yet. The discussion is really fairly generic, and that's part of the beauty and the power of the bootstrap method, that this general pattern is simple enough that it can be applied to many situations. Let's take a look at using it in a concrete example by loading a data set that we've looked at already, which is NBA data for the 2018-2019 season. This is the number of points from each player, and these are a number of features. We're going to focus on the following features only to try to make a prediction of the points. So we're going to pick field goals, the number of shots a given player made, field goal attempts, the number of shots that the player attempted, the proportion of free throw shots, the number of three-point shots that the player took, and the number of assists that the player had. So with these 5 features, we're going to try to predict the number of points that that player ended up having on average for the season. So this smaller data frame has its last column is the score, and then the first 5 columns are the features that we've listed. Now, obviously, there is a correlation between these two. First of all, this number cannot be possibly greater than this one, since only attempts at most, if somebody had perfect performance, they would be the same. But in general, you miss some shots, which means the number of attempts has to be obviously greater than the number of actual field goals. And by the way, this is just for the sake of an illustration, because in practice, probably these two would be the points prediction could be made strictly from the field goals, given that they are so strongly correlated. But it's interesting to ask the question of how do we build a bigger model, and it's going to illustrate something that we want to discuss a little bit later. So we build our linear regressor, we fit it with the design matrix, which is this part of our data frame, and we give it, remember, your pandas, and we give it the last column, every row on the last column, which is the points column. We could do this equally well by grabbing the points column. We fit that into our model. It turns out that the fit appears to be quite good. Our square value is nearly 0.90, almost 0.99. So let's take a look at the coefficients, right? Remember, these are the names of the various features that we used, and these are the coefficients for those. So as you can see, something interesting is happening, right? These are the coefficient for the field goal assist is 0.03. It's a very, very small number. So it would appear like the number of field goal attempts doesn't matter a lot, because it carries a very small coefficient in front of it. So the question is, obviously, why is that happening? Because you would think that the number of attempts made by a player would have a pretty strong influence in the number of points that they actually end up scoring, and yet it appears like the coefficient is somewhat small. If we want to know whether the model is consistent with this coefficient being 0, meaning with not having this feature not actually having any predictive value for the score of the player, we can go ahead and use our existing confidence interval function, right? What this confidence interval function needs is our sample, right, our data, and an estimator, right? Well, in this case, our estimator is precisely this, right? Our estimator is going to be given data, which obviously has to have the same structure. It will compute the regression by using the same exact fit that we used above for this particular data that it is given, for the data that it is fed. Whoops. For the data that it is fed, and it will return the value of the coefficient with index 1, which is this coefficient right here, right? So if we run this, well, indeed, we see that this confidence interval does include 0, right? The value for the coefficient was 0.03, and the confidence interval ranges from 0.13 to minus 0.05. So it does include 0. So it would appear, in fact, that this feature is not predictive of the point value, at least, or the model we have is consistent with this feature having a coefficient at 0 at this confidence level. Why that is the case, we will leave that here for now, and we'll revisit that question in the next section.